All right, so in this video, we're going to be looking at calculating surface integrals. And so we're going to be starting with calculating surface area and then continuing on to flux through a surface. Because the way that we set up surface area integrals is going to be related to the way that we calculate the surface integrals themselves, at least by using the definition. Now, the simplest type of surface integral is just the surface area. And so this formula is basically integrating over the area for the ds of our problem. And the ds component is going to depend on the vector, which is perpendicular to the surface. And it's going to have to be of a particular type perpendicular to the surface. Now, for rectangular coordinates, we're going to find that in a similar way to the way that we would find this for the normal to the surface that we need for the coordinate plane. Although for the coordinate plane, we don't have to be quite as careful because we can stand any normal to the surface, whereas for this example, we actually need a particular normal to the surface where we put all of our surface components on one side of the equation, but it needs to be in explicit form. So it's z minus the explicit form of our function in terms of x and y. So we can't just like take a sphere and just find the gradient of that implicit function. We would need to solve for z first and then move everything to one side of the equation. That would get us our big G, and then we could find the gradient of that for this application. So in this case, our gradient of our G function is going to be, based on this example, negative the partial derivative for little g and the I component, negative the partial derivative for y of little g in the j component, and 1 in the k component. Now, if we were to switch this order, little g first, then minus z, that's okay. That sometimes we'll care about upward pointing versus downward pointing gradients. We don't need to worry about that for the surface area, but we will in some of our other surface integral problems. And so I've chosen orientation that will be most likely to be consistent with those other problems that we're going to do. But when you put this into your essentially your arc length formula, the magnitude of your gradient vector, all of these negative signs are going to cancel out. So in this context, it doesn't matter the orientation, but this is oriented upward in this context. So our area formula is basically just the magnitude of this normal vector and then integrated over our area. And our components should just be in terms of x and y at this point. And so we can integrate in just x and y. Now, or maybe a different coordinate system. So here we're going to calculate the surface area of the function of xy, which is a hyperbolic paraboloid, over the region inside the circle of radius 4. So x squared plus y squared is less than or equal to 16. Now, the fact that our gradient is going to turn out to have x squareds and y squareds in it, and the fact that we're integrating over a circle is going to be consistent with the idea that we're probably going to switch to polar or cylindrical coordinates for this. But here we're going to take our function, we're going to put everything on one side of the equation, z minus xy, that's our big F function in this example. The gradient of that is going to be negative yi minus xj plus k, and then our magnitude of that gradient becomes y squared plus x squared plus 1 under the radical, and then we're going to integrate that over our circle. So we're going to convert this to polar form. X squared plus y squared is r squared. We get r dr d theta. Our circle is from 0 to 4 and 0 to 2 pi. This is just an easy substitution problem. We let u equal the thing under the radical, R dr is 1/2 du. We have u to the 1/2, and then we end up integrating, getting 1/3 r squared plus 1 to the 3/2, and then plugging in 0 and 4. And like many arc length problems, our surface area problems also end up with these weird 3/2 powers and stuff. Now, the integral is basically the same thing. It's the gradient of that normal vector integrated over the area. But if we have a parametrized surface, then we have to find that normal vector in a different way. So just as we would for the tangent plane, we have to find our partial derivatives for u and v, and then do the cross product in order to obtain that vector that we want. So in this case, here is our parametrized surface, and they've given us the limits in u and v directly. We're going to take our derivative here, and we're going to take our derivative for u first. So the u drops out here, the u drops out here, and the u drops out here. And then in the derivative for v, our cosine becomes minus sine, our sine becomes cosine, and then the k component has no v in it, so it's 0. And we plug that into our cross product expression, and we start doing our cross product. So here we get 0 minus this, so we get that. And then in the j component, we start out with the minus, and it is this plus this. And then in the k component, or this plus this rather, sorry. And then in the k component, we get these two cosines and these two sines, and we factor out the cosine squared and sine squared, and we get left with 16u. And then to go into our integral, we take the magnitude of this sucker, and we end up with this crazy expression, which then turns out to simplify a little bit. We can pull out our square root of 17 and the 4 that this reduces to. The u stays behind, and when you integrate this from 0 to 6, and then there's no v in the expression, you integrate from, you multiply by 0 to 2 pi, you end up with this expression for your surface area. Now, when we go into surface integral problems, we have to deal with other kinds of functions being outside of our d big S. So we're going to have either f of x, y times our ds, or f of x, y, z times our ds. So for instance, these functions could represent the density function of maybe the mass on the surface. And so we might be calculating the total mass of our sheet as the density changes. So that's a possible application for this. So for instance, we need to set up the double integral needed to calculate the surface integral x squared minus 2xy ds on the surface S given by this upside down paraboloid from 0 to 2 and 0 to 2. Now we already have a function of x and y already, so we don't need to do anything in terms of like getting rid of the z function, but we do need to calculate the ds. So that's going to be calculated the same way as our previous example. We're going to put everything on one side of the equation. We already have a problem that's solved for z, and then we're going to find the gradient of that, and then that ds in our integral will get replaced by the magnitude of this gradient vector dy dx. And we can integrate then from 0 to 2 and 0 to 2. Now, switching to polar isn't going to be terribly useful here. We might have to do trig substitution, but you can also try to use technology to simplify this. However, in this example, the problem just said set up the integral. It didn't say actually evaluate it. Now, another example might be, again, in this case, we have a z involved in our problems, But otherwise, the procedure is going to be very similar. We have z is x squared plus y squared. So this is a cone. Well, it's a paraboloid that's centered at the origin. And we're bounded by, again, this annulus essentially of radius between 4 and 2. Now, the big thing that we're going to have to worry about is that in our formula, anywhere there's a z, we're going to have to replace it with the expression for z for the surface. So step 1 here will be to take our xy over z and turn it into xy over x squared plus y squared. So the z has to come out. And then we're going to find our gradient. Again, same deal. We put everything on one side of the equation. We calculate our derivatives, and then we find the magnitude. Now, in this case, we're integrating over a inner radius of 2 and an outer radius of 4, and 0 to 2 pi. This one probably will simplify somewhat if we convert to polar, because we have xy here that'll give us an r squared, and r squared in the denominator, so those guys can cancel. And then we get an r from our dA, so r d theta, that will allow us to integrate this square root with substitution. And then we just have to worry about our thetas in the last step. So if we do our substitution, we end up with an extra 1/8 out here, which when we multiply by 2/3 turns into a 12th. And then we plug in our limits 2 to 4. And again, we get these crazy 3/2 power numbers. And then we're going to take that constant and we're going to multiply it by this integral. Or again, we're going to have to do a substitution for this. And we're going to get u is sine and du is cosine. We get 1/2 sine squared, and we plug that in, we get 0. Now, how do we interpret this 0? Well, that may be difficult to understand. If it's a mass density, mass can't be 0. So this would suggest that maybe there's some sort of problem. Our density function for mass should never be 0, should never be negative. But if we're talking about charge density, for instance, then this would indicate that there's equally balanced charges, that for as much surface area as is negatively charged, there's an equal surface area that is positively charged. Another possibility is we might need to use symmetry in order to calculate the absolute value of our mass density someplace, and then multiply that so that we can avoid this cancellation of the negatives. But we would have to investigate that further. But again, density problems really shouldn't come out to be negative, although there are contexts in which that is at least conceivable. Now, the next example that we want to look at is flow through a surface. And we have this integral vector field F dotted with the normal vector n ds. N is the unit normal vector to the surface. The unit normal vector is grad g turned into a unit vector. So this expression ends up actually partially canceling out with our expression for ds. And that ends up reducing our problem to either f dot the gradient g or f dot ru cross rv. Because remember, n is the gradient, for instance, gradient g turned into a unit vector, which has the magnitude of g, but then ds has the magnitude of g dA. And so, again, the two magnitude calculations cancel and leave us with just this. Now, to get the sign correct for the flow, we need to be using the upward normal to the surface, which is why I calculated the gradients previously with z positive, because that's the upward gradient. So here's our example. We're going to calculate this for the vector field given by this expression through the surface of the sphere in the first octant. So we're going to have to solve for z in order to get our g function. And then when we calculate our gradient for g, again, this isn't nice looking, but this is what we have to do to get the answer right. And again, taking the derivative with the square root, we end up with this chain rule thing happening. The halves and the minus signs cancel out. And then we dot the field with our gradient. And we end up with this expression when we simplify. Now, we should convert this to polar in order to integrate it. So our x squared plus y squared becomes r squared. Here's our r over here. So we can do a substitution. We're integrating inside the sphere, inside the circle from 0 to 6, and then only down to the plane. So the xy plane in the first octant. So the first quadrant of the plane. And then with substitution, when we plug these things in, we end up getting 216 for the r piece. And then when we add that to our theta piece, there's no trig functions in here. So we just multiply by pi over 2, and we end up with 108 pi. Now, if we're calculating the flux over a closed surface, then this will be similar, but we'll have to do a surface integral for each surface face bounding the volume, and then add the results together. And to properly orient the normal vectors, we want them to be outward pointing. So in this case, we're going to calculate the flux through the vector field here on the unit cube bounded by x equals 0, x equals 1, y equals 0, y equals 1, z equals 0, and z equals 1. So a cube of unit 1 in the first octant. Now this gives us 6 surfaces to deal with. Z equals 0 is the back face on the xy plane, and the normal vector pointing outward from the interior is minus I. X equals 1 is the front face, and the normal outward from the interior is I. The y equals 0 is the left face on the xy plane, and the outward normal is minus j. For the fourth side, y equals 1 is the right face, and the outward normal is j. Z equals 0 is the bottom face on the xy plane, and the outward normal is minus k because it's on the bottom of the cube. And then z equals 1 is the top face, and the outward normal is k. And so if we construct our 6 integrals, we're going to have our field dotted with I ds, which is going to leave us with just the I component, the negative of the I component. We construct this one, I ds times this. Again, we end up with the positive component. Here, again, j ds times this gradient field dotted with it. We get the middle component. And then here, j ds middle component, k minus k times the field. We get these two. Now, in the first 2 integrals projected onto the yz plane as a square between 0 and 1 respectively in both dimensions, so they're dy dz integrals, and we can replace x with 0 and x with 1 respectively. So this integral will go from 0 to 1. X is 0 though, so that gives us 0. But in the second one, we're going from 0 to 1, but x is 1. And so we don't get 0, we end up with 2. Now we repeat the same process for the yz plane. We replace the y's with 0 and 1 respectively. And in this case, though, there are no y's in here, and so we get exactly negative versions of each other. And so they become 0 when added up. And then finally, for our xy plane ones, we set z equal to 0 and z equals 1. This one has z in it in both cases, so the one with 0 becomes 0, and the one with, we substitute in for the 1, we end up with 1/2. And so the ones that didn't cancel out, we add the 2 and the 1/2 together, and we get 5/2. Now, terminologically speaking, when we get a positive surface integral like this, there's a net positive flow out of the region. And so this is referred to as a source because there is more going in than there is coming out. If we have a closed surface integral and the value is negative, then this is called a sink because that means there's more coming in than is coming out again. And if the closed surface integral turns out to be 0, we refer to this as an incompressible flow, and that means that there is the same amount going in as going out. Now, closed surfaces can be a lot of work, particularly if we saw in our example, we have a lot of bounding surfaces, and it would be nice if we could maybe convert this into a volume integral so that we don't have to integrate like over 6 different faces. And we actually can do that. That's what the divergence theorem does. It says that for a closed surface, the surface integral that we were just calculating is actually equal to the divergence del dot f over the volume. So we're going to redo our previous problem in using the divergence theorem here. So first, we're going to calculate del dot f. So we're going to take the partial derivative for x to get 4y. The partial derivative for y, we get 0. The partial derivative for z, we get y. We end up with 5y for our function. The volume is just a cube, and so we're just in the first octant, and so we're just going to integrate from 0 to 1 and 0 to 1 and 0 to 1 of 5y. And when you do all of those integrals, you also get 5/2, which is the same answer that we got from doing 6 different integrals in the previous version of this problem.